Good morning, good afternoon, good evening, everyone. No matter where you are, welcome to today's AIMEDx webinar. I'm Hongliang Xin, Professor of Chemical Engineering at Virginia Tech. It's my great pleasure to introduce our speaker, Professor Andrew White, who is really at the forefront of AI for science. Professor White is the co-founder and head of science at Future House, a San Francisco-based nonprofit research organization founded in 2023. He's also a tenured professor of chemical engineering at University of Rochester. Andrew received many awards, including early career investigator honors from NSF and NIH. He has served on the National Academy's Chemical Sciences Roundtable and multiple scientific advisory boards across biotech. He has contributed to the ongoing debate about safety of AI as a GPT-4 and 401 red teamer, speaking at multiple policy summits and visiting the White House in 2023 to advise multiple agencies. Today, Andrew will share how Future House is pushing the boundaries of what AI can do in scientific research. To everyone tuning in, thank you for being part of this growing community. We will have a Q&A session right after the talk. So please feel free to drop your questions in the Q&A box throughout the whole session. And without further ado, Andrew, the virtual podium is yours.
Thanks so much. Happy to be here. Happy to be back at a chemical engineering event. That's my background, chemical engineering. I'm going to share a little bit of results from Future House with you all today. Let me start by talking about what is Future House. So Future House is a nonprofit funded in 2023, primarily backed by Eric Schmidt, although we receive funding from other organizations like Open Philanthropy. We have a lab. It's the lab in the background. We had this idea that basically having a lab would be an important part of making sure we're grounded in working on AI for science. And we're in person in San Francisco and about 20 employees. So I'm going to talk about a couple things here today. One of them will be about motivating, like why AI for science is not just about accelerating, but also to kind of address some growing problems in science. And then I'm going to talk a little bit about what do our AI systems and other frontier systems look like today. And then I'll talk a little bit about the pace or the rate of change in AI. And specifically, we'll talk about reasoning models at the end, which I think are kind of a different or kind of a new direction that we're moving forward in AI. So science is changing independent of AI. This is a plot of the number of papers submitted to arXiv per month. And you can see that basically we've grown from 5,000 to now 25,000 today per month. And ChatGPT is shown on here, and you can see ChatGPT coming out didn't really change this. This has been a trend that's been going on in science independent of AI or any other trend. Here I'm now showing you the average number of co-authors on a paper. So in the 70s and in the early 80s, one was the average number of authors on a paper. And then now we're up to 4.2 in 2021, and I think it's probably closer to 5 now. And so it's not just that there's more papers, but also the complexity is growing, requiring more authors to be on a paper. And so you can look at this in a lot of different domains, right? So we know there's more papers. There's 5 million papers per year. It's probably closer to 7 million per year now. There's 250 million papers already out there in peer-reviewed literature. Data sets are getting cheaper, so it's now down to $200. Actually, some people tell me it's down to $100, but basically, it's $100 or $200 to sequence the entire genome of a person. So we're down to this point where you can pay $1. So you find $1 on the ground, you pick it up, and you can get a gigabyte of sequencing data. So it's not so much the case anymore that you as a person can really look through and get familiar with your data. And there's this measure which has been argued about. I think there's actually another discussion about this in Nature a couple of weeks ago. But basically, you can view the productivity in science going down from a few different directions. This paper from Park and Funk basically argued that papers are declining in productivity, so or disrupt, like how much a paper is disruptive. And they looked at this a lot of different ways, but basically they looked at a fixed number of journals, saw how often new papers come out that displace citations of old papers, so kind of replace them in the record of being like how mitochondria works or how, heterogeneous catalysis works. And so over time, that like sort of a new foundational paper has been declining. And there's other measures of this, like the time from when a Nobel Prize awardee's work is done to when they receive the prize is growing, meaning it's harder to distinguish what work is truly, revolutionary. And also the productivity in pharma R&D, which is another sort of direct measure of our ability to do science, has been going down and declining over the last 20 years, where now the cost of a drug is gone up much higher, and we're making about the same number of drugs per year as we were 20 years ago or 30 years ago, despite a lot of innovations in our ability to do research. And one reason that this could be is that the next discoveries are just getting harder and harder, right? We're basically pushing the frontier of knowledge, and each additional discovery requires more tools, more people, more insight than the last. And so, I mean, just some things coming of biology, which is the main focus area of Future House. There are really hard problems, and it's not surprising that it would take a lot of incremental papers rather than just one big paper announcing the discovery, and a lot more co-authors and a lot more time to really accomplish the goal. So that leads us to the mission of Future House, which is automate scientific discovery. And I will say that automate doesn't mean that like we don't want a person to participate in the process. It really means accelerate discovery by automating parts of it that we think are newly automatable. Certainly, there's been a lot of great work in automating like robotics and lab automation. A lot of great work in things like cloud computing or additional simulation tools. But we want to really see if we can go after the parts of the intellectual process of scientific discovery and automate them. Okay. So one of the things we always like to check is that, can LLMs already do science? This paper is, gosh, I think it's a year old, so maybe this is no longer relevant. It's the pace of the field. But basically, about a year ago, we started looking at can frontier LLMs really do biology research? And there's a lot of measures that people use. There's things like GPQA, MMLU, HLE, and these are all like data sets that people try to use to assess LLMs. So we look to see at MMLU Pro, which is still reported out today from frontier models. And so here are some questions, and you can all think about these yourself to see if you can beat an LLM. So here's a question on medicine. As of 2017, how many of the world's one-year-old children today have been vaccinated against some disease? Really, I don't know what kind of fundamental knowledge of medicine or biology this question tests. Here's one on history. I think this is a fun one. On which continent are most of the Venus figurines found? If you remember Venus, the god of the Greeks or the Romans, actually I don't know which, but certainly you wouldn't be finding these figurines on Australia or North America. And here's the chemistry one. So this is literally the first question in the chemistry section. Find the logarithm of 3 to the 2. I really like this question because, I don't know if chemists are more natural log people or they're base 10 log, but certainly if they were base 2 log, this would be an easier question. But so these are some of the questions that people look at, and then they report out like, oh, our model does this well on the chemistry subset or this well on the biology subset. And I think this question is just not really reflective of the process of doing science. Certainly they might measure some kind of textbook knowledge, but I think if you have a model that is superhuman on these questions, it doesn't mean it will necessarily be useful to do scientific discovery. So we made this benchmark called Lab Bench, where we tried to go after like what are tasks that people actually run at by looking at lab notebooks. So with lab notebooks, we thought about things that we use in the lab. Most of it's on biology. One set that we used is LitQA, and LitQA was basically constructed so that to answer the questions, you have to find a specific paper and then learn something inside of a paper. So you can't answer it by just knowing titles and abstracts of papers, and you can't really answer it by just scraping the internet. So normal LLMs don't do super well on this, although we released this about a year ago, and since then somehow it ended up in the training data of many LLMs. So now they get like 85% without reading any papers, which is a sad thing, but you just have all this stuff in the field is a very moving, high velocity activity. So we'll have to make another benchmark soon. We also made table understanding and figure understanding. Again, like the traditional figure and table understanding before this benchmark, I would say is more like transcription. Like take a figure and then write the caption for it, or take a table and write what it's about. What we try to do is make questions where like you actually need to understand the image, or make deductions from the image, or like, learn something from the table. So after we built this benchmark, we found that like LLMs, so this is, like I said, this is a little bit older work. So the colored lines here are models that are a little old, like GPT-4o is an older model now. And we had humans take the test, so they're in like green. And you can see there's a big gap here. And I think once this was done, it kind of reflected our intuition is that the LLMs are not that great at these kind of scientific tasks. You can see that actually in table understanding, they do pretty well at. Now, since this benchmark came out, LLMs have continued to make progress on it. It's not a unique benchmark, just like most benchmarks. Like once you sort of put it out in the public, frontier labs start to measure it, people start to measure it, and then progress gets made. And so I think it's one of the highest value activities you can do is to put out a nice, clean benchmark, and that kind of helps push progress in the direction that your benchmark points. Great. So that is measuring LLMs, measuring frontier LLMs. Now, when this paper came out, basically at Future House, we don't really have the ability to train frontier LLMs. We can work with frontier labs and you can fine tune frontier LLMs, but it wasn't really pushing anything on the benchmark. So we worked on agents at Future House, and that's what we worked on for a long time. So let's go ahead and define what is an agent. So if we take some of the problems, like just a simple textbook problem, like here I have a math problem, and I reformulate how I want to approach it. So rather than just trying to answer the problem directly, or use like reasoning models where I use a chain of thought, I'm going to try to construct this as like an environment problem. Basically, I have my question come in, and I give myself access to a few tools, like a calculator tool, and like sort of a submit my final answer tool. That goes to the environment. And then I have an agent that basically communicates with the environment. That starts off by receiving what is the problem, then it does some calculation, and then it gets back the answer, and then can submit the final answer. It's a school holiday here. I don't know if it is for everybody else. Okay. So I guess my kids will just join us for a little while here. So basically this framing, of course, is all nice and it's great to have a framing. This led to some code. Sorry, the code is very tiny here in these plots, but basically we wrote a framework to sort of define agents and define environments. And so we used this to build up a couple ideas for what an agent should look like and a couple ideas of what are interesting environments for science. So what does an agent look like on the inside? Well, of course, it can just be an LLM calling tools. There's some like niceties to have more complex agents, like there's React, there's this like observe, orient, decide, act. There's agents that have like an actor critic loop. There's agents that have like a reflection. So I think there's like a lot of different paradigms here, and you can represent them all as like a stateless object. Yeah. Okay, so if we just sort of make the decision to go in this agent framing, and we go back to these things I discussed before, lab bench, you can see we get a gain on all of these benchmarks when we call tools. So these are just a few models we tested this on at the time. I will mention that what's interesting is that when you add tools to these LLMs, Haiku actually goes down in accuracy. So there's something about like smaller models that if you add tools and put them in an environment, they get confused and they actually have a decrease in their ability to answer questions. But otherwise, GPT-4o, Claude Sonnet 3.5, Claude Sonnet 3.6, they all improve when you put them in an environment. Makes sense. Now, one of the things I want to do is we want to actually, though, learn from these environments. So what we do is we take a bunch of these scientific questions. So these are all molecular cloning questions, which is a laboratory technique that's used in biology. And we have all of the agents do a rollout where they basically use the tools and then they get some response, like did they get the answer right or wrong? We can collect all the correct answers, and then we can just do fine tuning on those correct answers. And you can do this in a loop where you like take an agent, you run it, you get correct answers, you fine tune the LLM in that agent to make it do that behavior that worked well better. And then you can take that agent again and then roll it back out. And you can do this process, over and over. So here's two examples of this. On the left side, we're doing that molecular cloning. And each dot is like one round of this iterative process where we take the agent, have it answer a whole bunch of questions, and then we go and fine tune on correct responses. And over time, you basically get an agent that does better than a frontier LLM. So in this case, able to beat GPT-4o and Claude 3.5. Basically, we're working with an 8B Llama 3.1 model. So it's a pretty small model, and it's great to see, though, that we can learn from our success and failures on these environments. And we also did the same thing on LitQA. LitQA is a little bit different because here we're doing some literature research. And basically, you can sort of see a gain over time and the accuracy from this. So what's interesting, though, is to look at how these models answer the questions. So on the top left, I'm showing you where they started. So we gave it some demonstration trajectories where like a person or another model basically went through and answered some of these questions using the tools. And then over time, the bottom right here is like the correct trajectories that it ends up at over time. And you can see that it really does learn new ways of answering the questions. So it's definitely learning some new behaviors and new patterns. So it's not just sort of recapitulating the starting point. At the end of all this, you can do things like test time sampling. So you can do consensus sampling, and you can get these kind of like cost per performance things. So the frontier models, although we can beat them with these models, the frontier models are usually more receptive to consensus sampling. So like if you call Claude 3.5, if you call it 64 times and then take the majority vote of those answers, or if you call GPT-4o and take the majority vote of the answers, you get a nice gain that you get some gain, but not as much. But on the other hand, you're getting into the $10 per question or $100 per question range. And so it's not super cost effective. And so you can scale out these simpler models, on a per basis, like a per K per 32, they're similar. But with the cheap models, you can scale them up to 1,000, test time examples. I don't think I have the plot here. Basically, you can just keep scaling this 1,000 calls. This, would be insanely cost prohibitive to do without all the frontier LLM APIs. So we're done training. Basically, we end up with a trained agent. And then these two things, basically, we put them together and call it a crow. And that takes it an input, and then it tries to answer questions. So we have a few different crows. Basically, there is crow, which is on our API, which is like a literature research agent. We have protein crow, which is a protein design agent. Chem crow, which is basically one of the classical agents that we put out a long time ago for doing chemistry. We have a data analysis crow, which basically can try to generate new discoveries from data. So I'm going to show you guys just a quick demo of Protein Crow. So Protein Crow is something that uses like existing deep learning models. So it has access to like bolts or arc diffusion. It has access to our other agents. It could do things like dynamics, literature research. And so this is just a very simple example, like design 92 binders for PD-L1. We'll just see if this video plays. So here I'm showing you like the setup. So it's trying to design binders. So the top left is like the binders that it has selected to bind to this protein. On the middle, we have like the tool it chose and some rationale about why it chose a tool. On the right-hand side, we're seeing like outputs from the tools. So here it's calling arc diffusion. Here it's calling MPNN. It might call this like target hydrophobicity tool. And basically over time, it accumulates a few different proteins that it thinks would bind to PD-L1. So we have a wet lab at Future House, so we can test out these designs. So we tested out these designs using cell-free protein synthesis, and we did find indeed that it binds to PD-L1. So we come up with a novel binder, which is great, and it's something that takes in natural language and outputs this kind of thing. So we should have a larger report out on this, and there's some cool things you can do with this. You can say things like, don't use alpha sheets, or like make an interesting secondary structure, or make it, at least 8 mutations away from any known binder. Okay, so that was sort of the setup of an agent. So we have put out agents onto our platform that anyone can use now. These like Phoenix and Finch and Crow. What we really like to emphasize is that you can see all of the steps that the agents take. So here's an example: propose a molecule that smells like fresh cut grass and binds to HER2. And you can see like what the agent thinks about and what tools it calls and what the output of the tools call. And you can get some insight into what's happening with these agents. Okay, so now I'm going to do a little bit of a deep dive on one of our agents, which is PaperQA, which has been a really successful agent for us on a lot of different projects. So PaperQA2 is the name of the version we use right now. And these are just some of the tools. We have more tools now, but basically the key tools are that it does searches over things like Google Scholar or Semantic Scholar to go find papers or our own set of papers. Then what it does is it uses something called gather evidence, which is it reads the papers. So it downloads the papers, parses them, and it reads them and finds which pages from papers, which sections from papers could be helpful to answer a question. Then it does citation traversal. It sees what things it found were helpful, and then it looks up who cited them or what cited them and pulls them in. And then it has tools like look for clinical trials, do a search on open targets to look to see if there's any interesting human genetic data that could help answer a question. And then it generates the answer at the end. Here's like a little demo of what this looks like. So here the question is, has anyone used LLM agents to automate the discovery of a novel molecular chromophore? So here is through the literature. So we have a bunch of titles. So that is sort of the process. Here that's animated a little bit more detail. This is what happens on the platform, FutureHouse platform, if you use it in your own research today. So we took like QA again, and then we had humans. We hired PhD biologists to answer questions on Lit QA. And a lot of times I say biology or biologists and stuff like that, but this is a general tool. It doesn't have to be in biology. And basically this system answers questions better than experts in the field. So we came out with our first version of this benchmark and the first version of the tool in January 2024. We had about 37% accuracy, so we were not superhuman. But then in September, we reached human level. And then in January 2025, we basically exceeded human level and got up into the 80s using test time sampling and basically modern LLMs and better ability to retrieve papers. So you can see this nice sort of steady progress to where now it's superhuman in its ability to answer questions. Of course, answering these like multiple choice questions is not a reflection of what is the scientific process. So we also checked to see if it could synthesize information from a domain. So here we're looking at, can it write Wikipedia articles better than human written Wikipedia? So we did is we wrote Wikipedia articles on topics, and then we took the real Wikipedia articles, then we like blinded evaluators to which source they came from, and we asked them which ones like more correctly summarize existing literature. So we're not looking at diction, we're not looking at the style or comprehensiveness, we're just looking at which ones reflect the cited papers better than the other. And our system actually had a lower hallucination rate than human written Wikipedia. So what we did is we then wrote Wikipedia articles for all of the protein encoding genes. So your human genome has 20,000 genes that make proteins, and Wikipedia covers about 3,700 of those genes. So we wrote the sort of remaining ones and put them up on a website called WikiCrow, which has basically a description of all the information in literature about all these different genes. One of the cool things you can do with this is contradiction detection. You can basically put in a claim, and then this literature agent will go through and search the literature to find out if anyone has ever contradicted that claim before. Doesn't mean that the claim is wrong or anything, but it just helps you find out, are you in a space of scientific literature where there's disagreement about a topic? What we did here is we actually had humans validate these, and this became kind of a hard one, is that humans disagree on what a contradiction is. So basically we got, out of the 2.3 we found per paper, 1.64 humans agreed with, humans disagree with each other. So I think this is like a reasonable measure. Okay, so that was sort of a nice description of what one particular agent can do. So these agents are very flexible because you can basically put in a natural language prompt and they can go do all these tasks. The one that writes the Wikipedia articles, the ones that does the contradiction detection, the one that does answering these questions, it's all the same PaperQA2 agent. It's really flexible and it's cool that you can do that. But I think that agents represent sort of scaling out average intelligence. Like whenever you look at the response from these agents, they look like what a human might do. The steps it takes are kind of like what a human would do, and we benchmark them against humans, and we see that they're comparable to humans. But really what we want to get at, though, is something that is truly complementary to humans, or is thinking in a way that a human would not come up with. And so that led us down this path on what are called reasoning models. And so I want to talk a little bit about how we tried to build it. We succeeded, but how we built a scientific reasoning model. So I've talked about a few topics for how you train LLMs. So pre-training is the traditional scaling law. Basically, you insert more data and more compute, and you get out, gains from that input. And we know that it's logarithmic. So basically, you need to 2x your compute to get an increasingly or a decreasing marginal gain on accuracy. There's scaffolding. Scaffolding is like what we do when we build an agent. Basically, when we put it together with tools, put it in an environment, give it the information it needs to know. And that is another way you can improve the accuracy of LLMs. And this requires like domain knowledge, not a lot of compute, not a lot of input data. But then there's reasoning models, and reasoning models are interesting. And reasoning here is like a synonym for reinforcement learning. So if you train reasoning models, you're probably familiar with this. They usually train with RL. But here, what we're doing is putting in some domain knowledge, and that comes from the reward functions we come up with. But it also is a lot less data and a lot less compute to get, the gains that you would get from pre-training. So just to give you, this isn't really a slide about how you train reasoning models, but just to show you like the effects. So there's this test called Humanity's Last Exam, and it was built like to be bad for LLMs. Basically, people wrote questions, and they wrote questions by making sure that LLMs couldn't get them right. They wrote very convoluted adversarial questions. And basically, it was meant to be a very difficult test. And if you look at like GPT-4o and Claude 3.5 Sonnet, those are the models they used when they were constructing this test. And then once the benchmark was released, basically O1 and R1 had come out around the same time. So you see a big gain from having reasoning models, but then O3 mini, and then the deep research tool, which is O3. These things came out and just basically gave a huge sharp increase in this test. So what's happening is that there's like a new dimension to scaling. Like you don't just do pre-training, now you can do reasoning. And that is basically giving us huge gains on a short amount of time because we haven't explored down this axis. So we're seeing very large gains in LLM's ability to answer these questions. So benchmarks are getting saturated much more quickly, which is surprising considering how fast they were getting saturated anyway a year ago. So let's take a look at what happens when you add reasoning. So this is sort of a little review on models. So on the x-axis, we have the size of models. So on the far right, you'll see these big models like R1 and O1 and V3, which is from DeepSeek. And then on the left, on the y-axis, you can see how good they are particular math benchmarks. We'll look at two math benchmarks averaged together here. And I set V3 as sort of the 0 point on this. V3 is a big frontier model released in December. It's about 670 billion parameters. And what you can see is that basically models that are red here are traditional pre-trained models, and they follow this kind of scaling laws that you kind of move up in model size and you get a gain in accuracy. And then in blue, we have the reasoning models, and you can see the reasoning models are all over. They seem to break this sort of scaling principle where if you, just increase the model size, you can see nonlinear gains in accuracy. So you're really breaking the scaling laws. So this is very exciting because scaling laws are in some ways for pre-training. In some ways they're nice because you have steady gains. In some ways they're actually terrible because it's like, okay, if I want to train a good model, I need to have $100 million of compute because that's what the scaling law says. So it's really cool that we can break out of this. And now on this line here, deep scaler is something which is about, I think, $50,000 to train. And it's at the same accuracy as V3, which is estimated to be $200 million to train. So you're seeing a huge delta between two models that have very different in their parameter count, their cost of training, but they have the same accuracy. Oh, I have the numbers here. So $200 million and 20,000. It's 20,000, not 50,000. Okay. And now, so reasoning basically helps at all scales. So here is the set of models, and we're showing that if you basically do if you make an equivalent reasoning model, you just get a gain at each size. So this is a very exciting outcome because we can basically escape this line. So the blue ones are on this line, that this logarithmic line that basically costs increasing amounts of compute. You can move away from that line by adding reasoning. So we wanted to know if we can do the same thing in science, right? This is all math problems. But if we could do this in chemistry, we could basically flatten the field and start to bring back frontier LLMs to the different domains. So that's sort of the goal, is can we build these? So let's see, what is a reasoning model, right? I'm talking about reasoning models. I'm saying they break scaling laws. What exactly is happening in a reasoning model? So a reasoning model is a model where you basically give it questions in any format you want, and then it will reason in natural language. It doesn't have to reason in natural language, that's how most people train them, but it reasons for a long time in natural language and then gives you a final answer. And the reasoning inside of it, what's different about it is that that is not trained. Like we don't have to get humans to write out their thought process, or we don't have to get like, thought processes we found on the internet. The reasoning, all these tokens in the middle that it uses to reason through, they're trained from just if the answer is right or wrong. So it's like emergent in the sense that it changes its reasoning just from what answers are correct or incorrect, not from any sort of intensive human grading process. So it's actually a very natural thing to train. Doesn't require a lot of structure. So here I'm showing you, I put in a chemical reaction, and then we see some of the reasoning. It's truncated because the reasoning traces are very long. And so it predicts the outcome of the reaction, and it gets the right answer from all these thoughts. So what can you do with a reasoning model? So we're going to talk about chemistry right now. So here's the reasoning model. Propose a one-step synthesis plan that uses commercially available reagents. So why is this interesting for a reasoning model? This is interesting because we can actually verify the correctness of the answer. So this is what I would call like an open answer problem. So there's not just one solution, there's n solutions to this, right? There's lots of ways you can propose how to make this molecule. And we can check a solution. So this is a verifiability thing, is that if someone proposes a solution, I can check it to see if it's correct by predicting the forward reaction. And I can check to see if I can actually buy, I can check to see if I can buy the compound with the database. So this has what's called a generator verifier gap. That is, I can easily verify the problems, but actually generating solutions to this is a little bit hard. And so it's really interesting if we can train a model to propose solutions to this problem. So the one, propose a modification to this molecule to increase its solubility about a 1 log S without affecting its scaffold. Again, there's many correct solutions here, and I can write code to verify solution, but generating the solutions is the hard part. So we built a data set of about, I think, and being 670,000. This is an earlier version of it. So we built a whole bunch of these tasks where we can verify the solution, but it's hard to maybe generate the solutions. It'd be very cool to have a model that can generate them. So some of them are things like, decrease the LD50 of this molecule, make this molecule have a better stability in the liver, or lower stability in the liver, predict the outcome of this reaction, change this molecule, but make the smell of it remain the same. We had some solubility ones, photoreceptor ones, like I want this molecule to have absorption at this wavelength, change it to have that property. So we built a lot of these different things. We took a whole bunch of source data. One of the decisions we made is we only wanted data that came from real experiments. So all the data is from molecules that were made in reality. Actually, I'll spend one more point in the slide. One of the things we had to do, though, is that to avoid reward hacking, we had to write what we call a reasonable molecule function. So the model over time learned to come up with very creative solutions to these problems. And so we had to write something that checked, when the reason model proposes a molecule, does the ring structure, has it ever existed before in nature? All the little functional groups on it, have those ever been made before? Because it kept proposing, wild molecules. So I had to write a little bit of a filter of is this a plausible molecule? And put that in the reinforcement learning process. So here we're showing, again, this is, I haven't updated this slide since our paper came out, I think 2 weeks ago. But so this is our accuracy across a lot of these different tasks. And, we get, very, very good accuracy on this. Our accuracy per reaction prediction is actually, I think the final model is around 80%. So our models in red here, our final reaction prediction is around 80%. So this is a little bit older one. Then we get all these multiple choice questions and these pKa questions. The pKa one has always been hard to predict pKa accurately. I think we ended up a little bit better at the end with the final model, but it wasn't really that exciting of a result for pKa. But we beat frontier models, which is really exciting. So basically trained on 500,000 examples, basically, and we're able to get something that's better than frontier models, better than humans on many of the tasks where we tested humans. So here's an example. Here's the input is take this chemical reaction and tell me what the output will be. And then it goes through and it reasons for a long period of time about what it thinks the right answer is. And one of the kind of exciting things about this work was we had a a really compelling result on data efficiency. So I'm showing you here like our in blue is our model, which is called Ether, by the way. We named the model like the day before we released it, so none of the slides have the model because I made the slides before we released it. So Ether is the name of the model. So Ether is trained through this process where we do rounds of like reinforcement learning and then knowledge distillation and reinforcement learning. So it goes through a few of these phases, and you can track to see how well it's doing in these different phases on one of the benchmarks. So this is showing accuracy and reaction prediction. And basically, after seeing like 20,000 examples, it's up to 50% accurate. And this is like, does it give the exact correct response considering stereochemistry? There's no flexibility here. So basically, it's an exact match agreement. Then over time, we get to like 60, I don't know, this is an older result, 67%. We ended up getting to 80%. But basically, we're only showing 50,000 examples through this process, and we're getting to accuracies that you see in like molecular transformers, where they're trained on, 500,000 examples or 400,000 examples. So we're seeing like a 10x reduction in the required data. So we go from 50,000 examples, sorry, we go from 500,000, which is what people normally train on, to 50,000 examples, and we're getting higher accuracy with this different reasoning model process. And the reason for this, like, some of it might be that we're training, we start from an LLM that has seen a whole bunch of chemistry data. So this is an LLM that has seen chemistry before, so we're not starting from scratch. Whereas like molecular transformer, it doesn't speak English, right? So it can't train on existing chemistry data, can't train on papers or like the internet. So it could be something in there. It also might be from this ability to basically repeat training examples. So in the reinforcement learning paradigm, you actually see the same problem over and over again because there's so many ways to solve it, because the reasoning traces are all different. So you could reason one way to solve a problem or reason another way. So you're less likely to overfit. So you get this kind of data efficiency. And we saw this across a few examples. So it's very exciting to see that we can basically dramatically reduce the data required to make a very strong model. Okay, so I think our paper, there's a whole bunch of information in the paper that talks about basically the steps to do. There's a lot of innovations we had to do. And then now I don't know if I'm going to do this again, but I put a little philosophy on the last few slides about this. So where do humans fit into this paradigm? Of course, we haven't really replaced humans. There's still a long way to go, but I think it's fun to just like think a little bit about what could be coming in the future. So one of the things is that, not just lab bench, but there's been many other domain specific benchmarks, and they're continuing to fall basically. Over time, this black line here is expert performance. There has been no stop in the march on improving LLMs. And I believe some people think that these benchmarks are, measuring the wrong thing, or that these benchmarks aren't really, a measure of like reasoning capability. But, we have tried to build benchmarks that measure exactly the thing. Like, it's like cloning scenarios here in yellow. We built this from laboratory notebooks of PhD students. We went to laboratory notebooks of PhD students, asked them what problems they tried to solve, took this information from the lab notebook and turned it to a question like, how would I solve this problem? How would I troubleshoot it? And so it really tries to get exactly the right thing. And basically we see that it's still falling to these models. And so I think a lot of people who are observers in this domain can say like, oh, the benchmarks aren't right, or the LLMs are learning the wrong thing. But people who are domain experts, we have tried to make benchmarks that really measure the exact right thing, and they always fall to these scaling laws. And so in that sense, like I just don't think there's no evidence to me that the LLMs are going to plateau or just not continue to get smarter in domains. So just looking forward, right, even with domain-specific benchmarks, LLMs are getting better and better. And if I encourage you all to go, regularly go to Claude or ChatGPT or Gemini and ask questions in your domain, and you should see a steady progress month to month of them getting better and better. And so there's a thought. I'm sorry about the swear word in it, but this is the author. The author wrote this, and this is from Wait But Why, which is a very nice blog about a few different topics. Basically, showing that the difference between a human and like a bird or a chimp is actually quite a bit. But the difference between the smartest human and the dumbest human is actually not a lot. And actually, this is interesting biology thing. Is that humans are much more homogeneous than other species. And so like there actually is not a big difference between very smart people and very dumb people. And And basically, if we can see this progress going, it's just going to swoop by the smartest human eventually, and then it will just keep going up. And it's kind of this, like, I think it's a fallacy to believe that there's anything unique about and the ceiling of intelligence for people. Like, basically, the limitations on human intelligence is a whole bunch of things, but basically there is no evolutionary pressure for humans to get to be as smart as possible. So basically, there's no reason we should imagine that LLMs will plateau at the smartest human. They should continue to keep going up. Of course, we've seen this in domains, right? Like in chess and Go, the AI systems that play chess and Go are just so far beyond humans, and there was no sort of stopping point. There was no algorithmic advancement that helped them go from, like, the best human player to above. Basically, they just continue to scale up. So anyway, I think we just have to reflect on the fact that we will not be the best at the domains that we're in, in perpetuity. So I have this like quote that I saw this first from Derek Lowe, but it's a very common quote that people say is basically, AI will not replace humans. Humans that use AI will replace humans that do not. And I think a lot of people operate on this paradigm. It's basically, AI is like a force multiplier. Like, if you're using AI and you're already pretty good at your field, AI can help you do better and better. And then there's this like, it brings up the floor in some sense too, is that like people who are not so great, or they're like new at their domain. So like if you're very new PhD chemistry and student, AI can help bring up your like floor of knowledge. And I think it remains to be seen if that's actually good or bad for education. I think I'm worried about that for education, but I think if you already know your domain really well, then AI is just like a net gain. But I think if you're still learning a domain, then AI can actually harm your ability to learn. And it also, I think, maybe doesn't give you the same boost that an expert will have. But then if you like think about it a little bit more, here's a change in this quote. So motor vehicles will not replace horses. Horses that use motor vehicles will replace horses that do not. So this is like, it's not so clear that AI will not replace humans and humans that use AI replace humans. So this is like, in history, it wasn't the case that horses learned to drive cars, and that's, how the field moved forward. It was the place that the motor vehicles just replace humans. And so I think it is a little bit naive to think that, humans will be guiding the AI process in all things. And I have like a little anecdote, is that when I was a PhD student, we went to the research librarian. We did this like orientation, we went to the library, and then basically the librarian was said, oh, well, you shouldn't use Google Scholar because you'll lose these valuable skills of going into the library and finding where the research journals are located. And then you'll look through the research journal, and if you learn to look up an issue and a volume number, you'll read some other articles, and it can be like really useful activity. And nobody uses the research library anymore. Actually, I tried to use it a couple of years ago, but I found out that the university had actually closed all the research libraries, moved all the journals to a warehouse, which then destroyed them all. So basically, you just can only use Google Scholar. And so I think there are a lot of these areas where basically humans maybe won't be the ones doing literature research, or humans may not be the ones writing review papers. Or assessing novelty. Maybe novelty is no longer the job of peer reviewers, but we basically take your paper and put it through a system that says like, yes, this is novel, or no, you forgot to cite these 5 things. Maybe those kind of activities will just be wholesale replaced by agents or LLMs. I'm not sure. But anyway, I think this is all good stuff to think about. Future House is a big org. Want to acknowledge, Sam Rodriguez, who's co-founder and CEO of Future House. I lead basically the scientific and technical work at Future House. And then Mike Skurlinski and Sam Cox. Sam Cox was the first author on ChemCrow, along with Andreas. And then Mike Skurlinski led a lot of paper QA2 projects. And with that, I think we have time for some questions.
Thank you, Andrew, for really, really excellent talk. So this is a Q&A session. So please post your questions into the Q&A box. I can see already the few questions come in. So Andrew, I will try to read it out, maybe paraphrase a little bit. Some of them are really long. Just make sure everyone can see it. So first question comes from Lane. So, do you think there's a diminishing rate of return for prompt engineering, particularly for multiple choice questions, versus the improvement to the actual training and architecture design? Is this the model actually answering a multiple choice questions indicate of its ability to do novel science?
Yeah, that's a great question. I actually think that yeah, I agree. Multiple choice questions aren't great. I would say that in the paper QA2 work and a lot of our agent work, we relied on multiple choice questions because it's just so much easier to evaluate. Basically, in a lot of scientific domains, if you say like, how can I solve problem X? There's so many solutions, you have to bound it with multiple choice questions to evaluate. Now, we tried LLMs as a judge in the past. Like an LLM tries to evaluate if the answer is correct, and they were pretty bad at it. However, that was, you know, maybe 2 years or a year ago. Now LLMs as judges are actually quite good, and so I think like you can get out of the multiple choice paradigm uh, uh, and get more of like a ground truth answer and compare it. But I agree, like to do novel science though, you need like really good hypothesis generation, and you need like really good, I think, data analysis or like ability to analyze results. And so we try to measure things like that. So we have a project on hypothesis generation. I don't have any results to share out with it, but I do agree that there's something like scientific taste or like, you know, the ability to know when is it an interesting research question, not an interesting research question. I have high hopes that we will be able to distill that out and have a model that can do the same thing. But I agree that like answering multiple choice questions is not you know the complete cycle of doing science. They're quite different. So yeah, I agree.
Yeah. Another question is, so nowadays there's several other tools like Copilot Studio, Amazon Bedrock. I will also add this MCP, these model content platforms that claim to simplify the creation and deployment of agent systems. So have you guys tried those type of platforms for building scientific agents? So they're curious about any advantages or limitations of those platforms, comparing you guys building the agents from the ground up.
Yeah, you know, this is a good question. So we at Future House, we tried in the past like LangChain, and we tried Llama Index, and we tried some other of these frameworks, and they're really great for prototyping demos. Basically, they're really good to try out an idea. And I think MCP now is, you know, a much better version of those earlier tools. What we found though is that if you want to get something that is trainable, like you can repeatably train it, and also something that is, I think, really measurable. We found that we just kind of had to go with our own, write our own framework. And the reason why we had to do this is that we wanted to really separate out the agent and the environment. And I think a lot of tools like MCP or LangChain, to go back to another one, they really mix the environment and the agent. So it's not really clear like what is like the part that you want to train. So like making a plan and critiquing the plan and reflecting, those are all parts of what I would call the agent. Whereas like the web search or like using this REST API, that's more of the environment. And so I think we try to separate those out, and that helps us like, you know, try different agents and then try different environments. But this is just, you know, this is an assumption. I don't think it's the right way or the wrong way. But what we found is that we can separate these two out, and then we can swap it, you know, to our scientific environments and things like that. But you know, right now this has been a good paradigm for us. Our aviary, which is the name of our like framing of this, that's been really successful for us, and all our agents that are deployed on our platform are built with this paradigm. But certainly there are, you know, lots of other turnkey ideas. I would say that the issue is that at some point you have to sort of like productionize or professionalize your agent, and that means like doing some benchmarking, and it means like really making sure you understand what is the input and the output to the agent. And we found that very simple systems work well for that. I think MCP and stuff like that, it feels a little bit stochastic, like it feels like it's hard to get repeatable performance. But certainly LLMs are getting so much better that this may all be moot, and they can basically, you know, consume a docs about how an API works and understand how to use it correctly, and they don't have to worry so much about having like a fixed, repeatable environment. So right now, our system is working well, but I don't think, you know, there's a right or wrong answer here, especially because things change so fast.
I see. So Christoph have a question regarding your point of data efficiency. So they argue a reinforcement learning trained model, while it has only seen about maybe 5,000 unique examples, might have seen billions of tokens in these examples throughout the number of reinforcement learning rollouts. So while the specialized models have seen millions of examples, but overall fewer tokens. Do you have comments on that comment?
Yeah. No, I think this is exactly right. Is that what we're concerned with at Future House is how many unique experiments we have to do in the lab to get to a compelling model. And so I agree, like my x-axis there is like chemical reactions that had to be performed and measured. But you're right that like we repeat looking at them. There's many tokens. There's a lot of compute compared to the other model I compare with. Like Transformer has much fewer parameters. It's much more compute efficient. There's no pre-training paradigm. So like we started that project from a Mistral model, which was trained on, probably trillions of tokens. So certainly it's unfair to say, in all viewpoints that it's more data efficient, but we're specifically trying to see how many experiments do we have to do in the lab to get to like a very good model. And I think if you're in a different domain, like if you're doing math or if you're doing programming, then certainly, it's very cheap to do lots of experiments. It's very cheap to get a lot of these examples. But when it comes to like chemistry or biology or material science, it's actually quite expensive and time consuming to do the experiments. That's the main bottleneck. And so that's the efficiency that we're excited about, that we can have data efficiency for that specific data.
I see. So question from Dan, amazing work. How can we get our hands on these tools? So besides of a Future House platform, you want to add a little bit more extra things to expand?
Yeah. So we have our platform.futurehouse.org, which has all the crows and it has an API, so you can try to use our agents in your own like workflows. Ether0, which is the name of the reasoning model we put out in chemistry, that's available in Hugging Face to download. So you can use that model. It's 24B parameters, so you can just about run it on your laptop if you have a modern MacBook, or run it on one GPU. It's not too bad. We also have a Streamlit app you can go to. If you just Google Ether0 and go to our blog post, it has all the links. There's a Streamlit app, you can just chat with it and see what it's like to have a model that reasons through answering arbitrary chemistry problems. Most of our code is open source. Almost all of our code is open source. We have Aviary and LDP, which is how you define agents and environments, respectively. We have PaperQA2, which is open source, which is an example of an LDP agent and environment, and it's got 8,000 stars on GitHub. It's very popular. We released the evals, so LabBench and Ether0's test set. They're both on Hugging Face if you want to test your own LLM agents or your own chemistry reasoning models. Yeah, so I think, trying to make everything open source. You can go to our website. We have like little blog announcements describing all of it. Our GitHub and our Hugging Face accounts have a lot of the code as well.
So Rob, have a question. What's the process of building Grow?
Yeah, so we have a tutorial on it. It's, I don't know, maybe 20 lines of code. Basically, you define your environment in one function, and that function just emits like the starting observation that you want to give to the LLM. And then you define tools. So you could define, 1 to n tools, and those are just with Python decorators. And then you then like basically bind it all together into a crow with one line of code. We then deploy it on our platform. You could do the same thing if you chat with us. We don't have that many organizations using our platform, but you could deploy our platform, or you could just use it on Python. And basically then you have like just a closed function that you basically put in the input, and then it will go through and then run through the tools in the environment and then give you the output. And that's basically the process. I would say it's a little bit more involved. I think there's people there's products that are out there that are even shorter that you can just basically pull in like well-known tools like a Python REPL and like a calculator. There's simpler ones. Ours, we just kind of balance. It's more flexible, so you can basically include any kind of domain specific tools that you want to have, and we try to be more explicit about how it works. But certainly there's harder and easier ways to do it.
Thank you. So another question is about the RM handling the numerical values. So what are the limitations when it comes to the size or scale of these numerical values, particularly in terms of how they tokenize the numerical data sets?
Yeah, this is a good question. So the decision we made in Ether0 is that we decided that the model always outputs a molecule. And that kind of helped resolve these questions because we were kind of nervous about this point. It was like, if it's got to like, take an arbitrary molecule and then tell you what the solubility is quantitatively or what the pK is quantitatively. We did worry about things like tokenization of the numerical value. So Ether0 takes as an input natural language or smiles or whatever, or numbers, and then it outputs a molecule. So we kind of avoided that question. I will say this question is a good question. There's this work on thing called like regression transformers, which are where you try to like use a different way of representing numbers to improve accuracy. But this, like most things in the field, has actually become almost not an issue anymore with the latest generation of frontier models. The latest generation of frontier models have much less problems with encoding numbers and representing numbers. So I would say nowadays it's not such an issue. I will say though that for like reading a table, I actually don't know what the status is of like, reading a table and turning it onto numbers. That may still be an issue, but I think working with numbers now is no longer such a difficulty. I think modern models are actually good enough now.
Yeah, another question from Qing Shao. So here in Drew, many LLM have the ability to understand the images as well. So any comments on how to leverage this?
Hey, Qing, it's good to see you. Qing was my lab mate when I did my PhD. Definitely it's something that we have thought about. It's funny that you bring this up because like it's always on our list of things to do is to like support like images of figures, but something always seems to come up ahead of it, like adding patents came up now on our roadmap before that. Having like better use of reasoning models came up before it, but definitely it's on our list of things to do. We do want to get figure understanding. It's not that hard. Modern models, like if you go to Gemini, you can just upload a PDF and Gemini will turn into images of the PDF and you can ask questions of the figures and it's pretty good at answering them. Definitely, yeah, LLMs can do this. We just haven't implemented it yet. It's on our list of things to do.
Yeah, so using LLM as a judge, so how do you go about designing rubrics? So what's a good sample size for domain-specific benchmark in general?
So for LLM as a judge, this one is, I would say, don't ever just give it a rubric. We find that to be really problematic. I think you want to give it a ground truth answer. So if you like have a question and you know the answer, write down the answer and then tell the LLM like judge it against this ground truth answer. And of course you can give that a rubric, but definitely having ground truth is key to that thing. And then it becomes like, oh no, how specific is the question? How specific is the ground truth? That's not easy. What is a good sample size for a domain specific benchmark? I would say we have like operated even at the size of 50 questions is okay. Now, if you go and you publish it, everyone's going to want it to be in the hundreds, I think, to be taken seriously. But I think you can start making progress with about 50. But it depends on the domain, depends on where models are. I would definitely say start at 10 and make sure you have like, make sure the models don't get 10 out of 10 and don't get 0 out of 0. They get somewhere between 0 and 10. So that can be an issue. You can make a benchmark and find out that the LMs either ace it or they get 0%, and then you don't have any understanding of what to improve or how to improve it. But yeah, I think 50 is a good starting spot for internal use.
I see. So another question is also the question I have. So current agent focus on the chemistry and the life sciences. So what's your vision for scale in terms of disciplines? So do you plan to extend future house AI agent to other disciplines like engineering, physics, and social sciences, and with new specialized agents?
Yeah, I would say like right now we have Owl, Falcon, Crow, and these are all domain agnostic. You can use them right now, and people do use them a lot for material science. And Owl is like precedent search, like has anybody done something before? So trying to see if something is novel. So Crow and Falcon and Owl, they all work in all domains. For making a specialized agent for physics or engineering, I would say that the closest thing we have is Finch. We haven't released Finch, but Finch is this data analysis agent, data analysis Crow. That one works with arbitrary data and it builds a Jupyter notebook progressively over time that then like gives some sort of evidence for a hypothesis or evidence for a discovery it's made from your data. That one I think could be quite general as well. But one of the things we like to do is we want to make sure that everything we do at FutureHouse is grounded in real experiments. And so just for cost purposes, we have just about lab. We don't have a physics lab and a material science lab. And so a lot of times we have a natural focus on biology problems just because we want to do an experiment in the lab that reflects, the hypothesis or the experiments planned by our agents. So I would say
Mhm.
I do pay attention, like Mike Skurlinski, who leads Paper QA2 right now, he is a material scientist PhD. And so he asks all of his questions in material science. So it's most of the stuff we do is pretty general, but yeah, I think we're probably going to
I
stick
see.
with biology as the end goal for now because we have the lab and can run the experiments there.
That's great. So where should we invest more time and effort in advancing LLMs toward actually contributing to the scientific progress?
Yeah, I think that's a good question. Certainly, I think working with literature is a great high value activity because the scientific record is natural language, and LLMs are really good at natural language. I think reasoning models are very intriguing to us. Like we've never had interesting, like super interesting ideas come out of agents. Basically, agents do a good job on tasks and follow instructions very well. But the reasoning model has started to produce really unusual like ideas, really interesting molecules. Like it really feels like a different direction for science. So I think making reasoning models for domains is a very exciting activity. Um, and then I think benchmarks though, like if you really want to advance LLMs and you don't have a lot of computer, not a big team, one of the best things to do is make a good benchmark, do a good job, put it on Hugging Face, announce it to the world and get buy-in from the people. And that is like a great way to steer the ship of LLM progress towards a problem you care about.
Mhm. Yeah, here another excellent question. So you mentioned the ability of AI to reach or even surpass human intelligence, like AlphaGo. But for science, this loop can be super long, which makes the reward very sparse. So what's your vision on this closing the loop for scientific agents to be able to reach or even surpass human intelligence?
Yeah, that's a good question. Certainly, if it comes to curing a disease, the the cycle from the biology idea to the phase 2 or the pivotal trial is 5, 7 years. So certainly the cycle times are very long there. On the other hand, there are things where the cycle times can be, hours, where it's like, okay, will this protein bind to this protein, or what would the yield of this reaction be? Well, I guess maybe the yield's a little harder. What would the product of this reaction be? I think it depends on the topic, but we're pushing these data efficiency things, right? The data efficiency plot we showed, that's us trying to get at this, like, can we get to lower requirements of data? Um, and then with the agents, I have written a paper with people at University of Rochester on in-context learning with catalyst design outcomes. So you basically design a catalyst, you find the outcome, and then you put it in context for the next experiment. And that's been successful. So I think there's a lot of flexibility with LLMs and trying to get data from different directions. But I agree with you, it's like AlphaGo and AlphaZero. These models certainly benefited from the fact that chess and Go are very rapid and they can have self-play. Science is not a self-play activity.
Mhm.
So I think we'll have to be creative. But yeah, this is a good question, and I don't think I
Mhm.
haven't solved it. We haven't solved it yet. It's something we're paying attention to.
Mhm. I see. So another question, can you please share your thoughts about the ability of these LLMs, especially the reasoning model, to extrapolate outside of the data they have seen? So most of applications involve interpolating among different variables. So would appreciate your thoughts on behavior when it comes to purely extrapolation.
Yeah, I would say that the reasoning models, we did a really good job of basically making sure that all the reactions that are in the test set had different products, and reactants than the training set. For the pKa, for like the LD50s, we also did like the scaffold splits to make sure that the compounds that are in the output are very different from the compounds training. So really try to measure extrapolation in that paper. I would say like an area of extrapolation though that I don't think we measured super well is like task extrapolation. So basically we asked it to do things like scent and LD50 and pKa and solubility, but we didn't go do like solubility and I don't know and octanol. Like we didn't do like log P, we didn't do partition coefficient and test to see if it extrapolates between tasks. That's an open question. We didn't really look at that. But certainly I think within a task, like within reactions, we saw good extrapolation, what you would expect from other models. Certainly, I agree that like one of the problems with machine learning and chemistry or material science is that chemistry materialists want to find the best material, like the unique material that really stands out. And in machine learning, you want average good performance across the domain. I think that's where you can use methods like Bayesian optimization or reinvent, these kind of other methods that really push you out of domain. And certainly reinforcement learning and reasoning models are examples of these things that you can really get wild molecules output. So that's why you have to do this like reasonable molecule, this like reward hacking checks, is that reinforcement learning really does produce like very weird and unique ideas. So I do think that there's more of a chance with reasoning models to get clever, creative, extrema than what we would see from pre-training or supervised fine-tuning. But yeah, I agree. This is always the issue is that chemistry is like you want to find the weird one example that breaks the rule and breaks the trend.
Yeah, we are already over time. So I have one maybe last question. So Future House initially chose to build with specific language model like Cloud. But later you guys have published the Ether Zero model. So what's your decision from Future House on this type of things using a custom model versus the fine tuning or prompt existing foundation models?
Yeah, I think the reason we did this is that well, two reasons. One reason is that like the LLMs, French LLMs, are still bad at chemistry. Like to this day, they still cannot predict reaction outcomes. They can't name molecules. They're really not that good at chemistry. And it's weird because they have a good intuition of chemistry. In fact, I'd say they have a great intuition for chemistry. But when you ask them to actually make a molecule in smiles, they just don't do a great job. So I think that's one reason why we wanted to try to make our own models, that we wanted to sort of get something that could actually generate molecules in a reasonable way. And the second thing is that with this flattening, like I showed in some of my slides, like these are the cost of reasoning models is coming down, and basically you have opportunity to get off this scaling. You're not stuck on this thing where you need 500 GPUs to be competitive, or you need 5,000 GPUs to be competitive. You can break out of that paradigm with reasoning models. So we also wanted to prove to ourselves that you can actually get scaling with compute and with reaction counts that is going to get you like a flywheel effect. So basically, now we have a goal of okay, well, the Ether Zero project was probably cost $50,000 of compute at the end, and it took about 50,000 experiments. If it costs $50,000 and 50,000 experiments for us to get an extremely good model on arbitrary tasks, that is so much more approachable. So we can go to things like predicting gene regulatory networks, predicting promoters, other things predicting catalysts, right? You can predict the outcome of the yield of catalysts. You can have predicting all these different topics with 50,000 examples. $50,000 is totally different. In fact, that's like the amount of money we pay on like LLM credits for some of the past projects we did from prompting or ICL. And so I think we're very excited about the fact that this sort of flattens the compute. So I'm very excited for that direction.
Well, that's really exciting. So there's no better place to end this webinar. Thank you, Andrew, again for the excellent talk, and stay for a longer time for answer all those questions. I hope to have you in person soon.
All right. It was great to chat. Thanks to everyone for listening.
Thank you. Thanks everyone for chiming in, and wish everyone have a nice summer break. We'll continue in the fall semester.
All right. Bye-bye.
Thank you. Bye-bye. See you, Andrew.